as I mentioned in the demonstration and introduction video, this chapter is talking about superposition of waves. Meaning if we have multiple waves in the same medium at the same time. Now they have to be the same type of wave. A wave on a string is not going to interfere with a water wave in terms of what we mean here. Superposition of waves just means what does the overall medium look like when there's multiple waves traveling through the same medium at the same time. What we saw with the demo is that the total displacement of the medium, I'll call it a D sub T for total. In the case of the demo, we had essentially what represented a snapshot graph. Our wave would have been traveling right to left or left to right, so horizontally. So X would represent where horizontally in the X direction, where we would be talking about the displacement, and T is at what time. Individually, wave 1 would have a certain displacement at a certain location and certain time. Wave 2 would have a certain displacement. The overall total displacement of the medium, this total displacement, depends simply on what wave 1 is doing to the medium at that location, plus what wave 2 is doing to the medium at that location. And technically, we could have as many waves as we want to talk about, all coming, whatever displacement they would be causing in the medium at that location and at that time would determine the overall resulting displacement of the medium. And that's what we're talking about when we're talking about superposition of waves. What does the overall wave look like if there's multiple waves in that place at the same time? Now, let me give you a couple other examples and visuals of this. So one of the PhET simulations, which you've hopefully seen at least one of them by now, this one just shows us the superposition of waves. So in this top row up here, we can choose these different frequencies. These are all considered A notes for anyone who's musically inclined. That doesn't matter. So if that means nothing to you, that's totally fine. Right now, we only have this A1, the amplitude of 1. So the middle graph, the one that's labeled harmonics, is what that particular wave looks like. It has a specific wavelength. It has an amplitude of 1. And so right now, the bottom, where it says sum, is showing us the same thing because we only have one wave. We don't have more than one wave to add together. If I add another one, so for example, A5, if I add that in here, I can give it whatever amplitude I want, but it has a different frequency. So the middle graph is still showing the original A1. It's now showing us A5, the second one. And the bottom graph is what we see because of the two added together. So this is essentially showing us the superposition of these waves. If I add a different one, I can add it up or down. Notice that just changes how those initial conditions. So this A3, since I went down to a negative amplitude, it oscillates going upwards first. But the addition, as we add these three waves together now, this pattern that we're seeing on the bottom keeps changing because it's adding all of these different waves together. The middle graph's getting kind of messy because it's plotting all of these individually. So we, at the moment, have 6 different waves represented in the middle graph, but the bottom one represents the summation of all 3. So just to give you an idea of what we're looking at, superposition is simply the summation of the displacement of however many waves are in that location at the same time. Now, this Fourier series, if you get into analyzing frequencies, like in electrical engineering, or if you go into something that deals with sound, you will work more with Fourier series. For now, I'm just using it to represent this summation, just to give you a visual of what we mean. In this chapter, we're going to also talk about what I mentioned with the demonstration, the perfect constructive interference, that's when we had the 2 identical waves. Now, it can be more than 2 waves. The demonstration only had 2, and as far as we are going to mathematically look at it, we're only going to look at 2, just to stay on the simple side, or the simpler side in comparison. So 2 identical waves, meaning they're the same type of wave, same type, same amplitude, same wavelength, which in turn means they're going to have the same frequency as well, and the same speed. To get the perfect constructive interference is when they are in phase with each other. So both of them have a peak at the same location, the trough at the same location. So when they're added together, we get one wave with twice the amplitude. It still has the same wavelength and same frequency. So we call this a maximum, or if it was sound, it would be the loudest sound. If it was light, it would be brightest that we would see. So perfect constructive interference, the waves must be identical. They meet up in phase to meet this criteria of perfect constructive interference. We will often drop the word perfect and just call it constructive interference and imply the perfect, just as an FYI. Perfect destructive interference and again, interference. We often drop the word perfect and just say destructive. It does also require 2 identical waves, or more than 2, meaning same type of wave, same amplitude, same wavelength. But these have to be out of phase. What we mean by that is wherever one has a peak, the other one has a trough. And I'm not drawing that very well. Let's try that again. So when we add them, we get no displacement at all. So again, a silly way to remember it, perhaps, is just they destroy each other. And that's really not what's happening. It's the positive displacement adding to the negative displacement. So a positive number plus the negative number gives us 0. But my silly brain, that was a way for me to remember. So when we talk about being in phase and out of phase, that is going back to the general wave equation. Oops, let's write it the right way. So kx minus omega t. This whole thing right here is the phase. We use phi to represent it. So phi naught is the shift that accounts for the initial conditions. Phi itself means everything within those parentheses. For perfect constructive interference, for a peak to line up with a peak, the phase shift can be 0. But if you remember the point in the video where I said, let's slide the bottom one and make sure this peak lines up with the next peak. If I move my wave over, I mean, granted, we have a section that over here that's not interfering because it's not in the same medium at the same time, and we'll have the original section up here. But in this location where both waves still exist, we still have peaks lining up with peaks and troughs lining up with troughs. So they are still in phase. In terms of an angle, that would be a shift of 2 pi radians. We've shifted it a whole cycle. This will happen at 4 pi radians, and so forth. And so we can say that the change in this phase, this difference in phase between the two waves, can be a multiple of 2 pi radians. So m means a multiple, a multiplier. There's multiple situations where these peaks can line up with the other peaks. So as we just mentioned, they don't have to be shifted at all. So m could be 0, but if m is 1, that corresponds to that shift of 2 pi. If m is 2, that corresponds to a shift of 4 pi. And we could continue this if we had, and the contraption I have, the actual demo I have, we can't have higher multiples. But in generic and general terms, that could be the case. So m is just a multiplier, just saying that there's multiple situations where the waves can line up peak to peak. Now, in the case of destructive, in order to shift from what was perfect constructive, so where the peaks lined up, oh dear, I'm not very good at drawing sine waves when they have to line up. So if they start out in phase, that's a delta phi of 0. No difference in their phase. But if I want to shift it so that they end up being perfectly out of phase, I need to shift this peak to line up with that trough. So now if I have a peak lining up with the trough, it's doing exactly opposite, then I get the destructive interference. So I essentially have to move this peak to where the trough was. That's half a cycle. In terms of radians, that would be pi radians. Now, to keep it out of phase, I would need to take this peak and line it up with the next trough if I wanted to move it farther. So that would be 3 pi radians. 5 pi radians would lead to destructive interference as well. So we can write this generically, that this difference in phase, the way we tend to write it is this way. M plus 1/2 times 2 pi. The reason for writing it this way is so that we can use these same multipliers, these same multiple values. So if m is 0 here, if I plug in 0, I get delta phi of pi, because I get half of 2 pi. If m is 1, 1.5, I get 3 pi. If m is 2, 2.5, I get 5 pi, and so forth. So we write it this way such that we can use the same multiplying values, same multipliers, and then we don't have to remember a different m value for one situation compared to another situation. Okay, we're going to build on this, but we're also going to talk about some specific situations where we see this constructive and destructive interference. So some applications is what we're going to look at. So we'll start, the first application we'll look at is standing waves, which we'll talk about in the next video. And then we'll also talk about thin film interference, which is also called optical coatings, and just interference in general if we go to a concert, for example, but on a very basic scale, because a concert deals with lots of waves that are interfering, and we're going to keep it on a basic level. So superposition, addition of the displacements individually give us an overall displacement of the medium. Perfect constructive interference, we get double the amplitude, same wavelength. Perfect destructive interference, we get no displacement at all.